Okay, so part of our mission is to put the ground-based GNSS receivers over this region. There are a lot of important scientific research to do here and to complete our global knowledge of the equatorial ionospheric region. So before we can get started, because of the numerous, I won't say failure, I will say incomplete mission that has been initiated over this region in the past, we wanted to start from a very basic level where we bring in everyone that will be involved. We get to know ourselves, and part of this is to build a network of people that can work together. And number one mission is to make sure we can work together because that will facilitate the installation of the instruments. And you can see that is a beautiful scene. And all of those points that you see there are real points, regions where we can actually put a autonomous GNSS receiver. So it's very impressive and it's an ambitious mission, and we hope to get it done by everybody's help on this platform. And yeah, here also we train and develop, we are involved in training and development of our members for ground-based instrument installation and data usage. That is why we bring in professionals to talk about several aspects, scientific aspects, instrumentation aspects to us on how we can use the data and get the instrument installed. Also, we are very, very interested in data accessibility. A lot of people, we understand how they want to keep their data for first use or novel use of the data, but when you allow your data to be used by other scientists, you'll be able to get more value for that instrument. So we on this platform, we encourage sharing of data and free data accessibility, which I think is a global need. So that is part of our mission here. So we have a lot of speakers that have been engaging with us since the beginning of the year. And now we are in May, and we have our special guest speaker today. Like I said, he will be introduced by no other person than Professor Rabiu, who has been working with him long time ago. I remember in those days when I happened to, Professor Rabiu introduced me actually to space science. And at his office then, he had a magnetometer, and we were to install that magnetometer, and he was like, oh, that magnetometer was given to us by Boston College. And I remember that up to today. That was like 17 years ago. So you can imagine the long relationship between these two friends. So we also have a lot of speaker outlined. Yesterday, somebody contacted me from Kenya Space Agency, and his name is Joseph Maruti, and he's very interested in the mission. And he said at Space Agency in Kenya, they are very, very interested in CONGA projects, and they are willing to host and be involved in these projects. So I asked him to actually give us a rundown of what the Kenya Space Agency is all about and what they are doing, their achievements. And so we agreed to do that in one of our meetings, which is on October 29th. So we're going to have this special visitor giving us a rundown of the Kenya Space Agency. Thank you very much, Mr. Dr. Joseph Maruti. So I think I will stop my short presentation and allow Professor Rabiu to introduce special guest speaker today. Professor Rabiu, the floor is yours.
Thank you very much, Dr. Jonah, for this opportunity. And I'd like to go straight to the point. It's always interesting, and like I said, it's a privilege to introduce someone who has been so dear to me and many of us in Africa. He has helped us, he has brought us up, and he has not left us alone ever since. And that is in person of Dr. Keith Groves. I call him the big boss, and he's still our big boss there. He holds a BS in physics from Andrews University and a PhD in space physics from MIT. And he's the principal investigator of the Space Web and Technology Application, FATA, Center of Excellence, and also he is the interim director of the Institute for Scientific Research at Boston College, where he's been working since 2011. Previously, he led the U.S. Air Force Research Laboratory's ionospheric research program, focusing on the effects of ionospheric disturbances on radio systems. At that time, he was the PI of SCINDA, which is very popular, the SCINDA GPS, and he installed the first ever GNSS receiver for space weather monitoring in African equatorial region at Cabo Verde, July 2006. And many of us, some of us were privileged to be there to witness that first ever installation. And it was from there that he deployed quite a number of GNSS receivers. That's the one Dr. Jonah was mentioning. And actually, it was a GNSS receiver that we installed in November 2006 in Nigeria. That came from him. And SCINDA became so popular over Africa, and many of our PhD graduates today use the data to do their research. Well, Dr. Keith Groves, the big boss, permits me to call him that. I really call him by his name. Has received numerous awards for developing a global real-time scintillation monitoring network and associated models. And he has also been involved in capacity building programs that started in 2009 at the Abdul Salam ICCP. On a yearly basis, we come together, and he's been teaching, tutoring us right from the beginning, and like I said, up till now. He is the chair of OSCE Commission G and has authored over 150 papers, establishing himself as an expert in ionospheric scintillation on radio frequency system. The citation given to me was so long, but of course I was advised by our covenant to squeeze out something so as to introduce this important personality who actually needs no introduction to many of us, but for the benefit of others that don't really know him, he is indeed an authority in equatorial ionospheric irregularity, and as well as radio wave propagation effect and remote sensing of the ionosphere. So it's my privilege to welcome a mentor, a leader by excellence, and a fellow of the African Geophysical Society, and that is our big boss, Dr. Keith Groves. Please, the floor is yours.
Thank you for such a kind and generous introduction, Babatunde. And, with regard to SCINDA and the whole development of that, I want to recognize the role that you played from the very beginning. You were the first guy to get a system and just to help promote the whole ISWE, the whole International Space Weather Initiative. Really, you did a tremendous job, and I really appreciate that, and continue to appreciate our relationship and the ability to work together still. So thank you very much for everything you did to help promote space science across Africa. Um, so I have more slides than I can get through. I wasn't sure exactly what to target for this audience, but I maybe have a better idea now. And I would ask if we want to do this, try to stick to maybe 30 minutes and maybe some time for discussion or questions. I don't mind taking questions normally in a room in real time. I prefer that, but on a virtual meeting, it may not be as easy. So basically, let me see if I can share.
Yes. Yeah, you could have 30 to 40 minutes of presentation, and then we go into the questions.
Okay, that sounds great. Let's see. So I'm just going to share my desktop. Okay. Can you see
Yes.
that? And now should be full screen. Does that look all right?
Sounds good. Excellent.
Okay, thank you. Thank you.
Mhm.
So yeah, my talk is going to focus on small scale irregularities and scintillation, and those two topics are tied together, and why they're important, basically, and some recent efforts that we have at BC in order to try to specify and forecast these, which go beyond some of the work that was done previously. Um, so yeah, so this is just an outline. What is scintillation, or the physics of scintillation, and some of the characteristics, the impacts on the systems. I'll at least show an example of that so you understand why it's important. And certainly the goal of CONGA to try to improve our ability to do this over Africa, which is an extremely interesting and unique environment, is a from both scientifically and from a systems and applications impact, is very important. So I want to talk about a new way that we are doing this using monitoring irregularities. So for specification, using radio occultations. And then I have a few words to say about our SPARTA activity, which is focused on forecasting irregularities, and also then the scintillation associated with it. So I may skip a few slides here. I may go fast in some places. We can come back if there are questions. But so basically, this is the space environment, and this is to scale. And where, this is the radiation belt, so this can be difficult for satellites. And again, a GNSS orbit is typically out here. They go through a lot of radiation belts. Scintillation activity is generated by what looks like a very thin shell right very close to the Earth, right? So the ionosphere is this region, um, you know, where the F region, the peak area that's causing most scintillations, is around 300 kilometers above the surface. So from the standpoint of this larger space environment, it's a layer of the atmosphere that's very close to the surface, and that's where these effects on radio wave propagation become important. It's this region, and it's of course related. And so what happens is, in terms of how the scintillation occurs, write down the equation for the delay of a signal coming from a satellite. There's the range to the satellite divided by the speed of light, right? So if you had a perfect vacuum, that's all that would be the delay between a signal being transmitted from a satellite to Earth. That would be the only term. But we have this additional term, and this is an approximate term, where that's actually due to the presence of the electrons. That's what in total here. It's the total number of electrons between the satellite and the surface, and it slows the group speed down, basically, of the waves as they propagate, and it's proportional to 1 over f squared. And that, of course, is why GNSS systems employ two frequencies because the delay due to the ionosphere is dependent on frequency. And by measuring that at two different frequencies, you can cancel this term out. At the same time, you get a phase perturbation, which is an advance. The phase is actually advanced as opposed to delay. And that term looks like this, again, dependent on the total number of electrons, which is just this integral along the path. So basically, if you have a uniform ionosphere, it's always going to slow the waves down, but it doesn't distort the amplitude in the phase. If you have irregularities, though, what happens? And we'll talk about that a little bit more. That introduces phase variations on the wavefront. And as it propagates, it causes a diffraction pattern on the ground. And because this is very dynamic and the ionosphere is drifting, a user on the ground is going to see rapid fluctuations of the amplitude and phase. And the key thing is this, if you're going to have diffraction, is the phase changes have to occur within a relatively small distance, which is known as the Fresnel scale. And that's shown below. So we'll talk about that a little bit more. I just want to set the basis for it. The ionosphere is actually a very small perturbation to the index of refraction for signals, GNSS signals that are at 1.5 gigahertz, for example, L1. And if you look at put the numbers calculate what this delta is. This is the index of refraction here. And it's just this F sub p squared, which is the plasma frequency squared. That's proportional to electron density, shown here, and the frequency of the wave. And when you put in the frequency for a GNSS signal, you find this is a very small perturbation. It's 4 times 10 to the minus fifth. So you say, for all practical purposes, sorry, go back if I can. Guess I got to use the buttons. For all practical purposes, this is still 1. And what I'm showing here on the right is if you took Snell's law and you just calculated what the bending angle would be, the red line is the wave coming in a vacuum, and the blue line is the continuation of that wave at L1 frequencies. Okay, so this is a very, very, very small change in the angle. It's microradians. By comparison, this is how much water would bend the ray path, and that's why you see a pencil in a glass of water looks disjointed and bent, right? With water, we see the difference. But in the ionosphere, you can't even tell. The refraction is so small on these signals that you would wonder that it could do anything at all. And yet the power of diffraction rather, is that even very small changes in this phase path can cause big changes in the propagation of the signal. And this same equations here, I just want to illustrate what's happening graphically. You can see the irregularities. That's what's represented by these blobs. And so different parts of the wave pattern are slowed down, or conversely, the phase is advanced. And so when you exit the ionosphere, you no longer have a uniform phase front on the wave. Different parts of the phase front have been adjusted by different amounts due to the irregularities in the ionosphere, these inhomogeneities. And as a result, as the wave propagates, it interferes with itself. And so if you put the frequency in, the delta phi for this is going to be a problem. It's very sensitive to the mouse, except when I want to go backwards. Is about 5 times the TEC radians. Okay, and so if you want to get a phase change of pi radians, that's 180 degrees. That would give you constructive or destructive interference, right? Then it turns out you need about 0.6 tech units. Oh, that's not such a big change, is it? We have 100 tech units during solar maximum over large parts of the low latitude region. So 0.6 is a very small change, but that 0.6 tech units needs to change. That variation needs to occur over a small spatial scale on the order of and less than a kilometer, right? So that's the trick. You need these to be very small scale irregularities in order for the diffraction to be effective as the wave propagates. You know what? I'm not going to take the time to go through this. This is a physical picture of the Fresnel scale. And just to give you an idea of why the Fresnel scale is important, why does it matter? And it's basically the distance over which, if the irregularities are over larger distances, as the wave propagates to the ground over that range, if the change is over larger than a Fresnel scale, you don't get actual constructive interference with the wave. And it just shows you, this first Fresnel scale is the really important region where the signal comes through. Beyond the Fresnel scale, you get phase mixing, basically. The phase changes so rapidly that it's basically noise. So the contribution comes, the filtering is done there. And in fact, at high latitudes, we frequently see phase scintillation, but not so much amplitude scintillation. When you don't have amplitude scintillation, it means you really don't have diffraction taking place. But if you have rapid changes in TEC due to high drifts, that can give you a very fast changes in the phase without changes in amplitude. And just the power spectrum on the right here is intended to demonstrate that. This is the spectrum of the irregularities, and diffraction occurs in this region near the Fresnel scale. The contribution rolls off quickly as you go to larger scales. But the phase scintillation, the phase variations due to just changes in the TEC, they can go on indefinitely, right? As you get larger and larger scales, you have larger and larger phase changes normally, and as it drifts by rapidly, right? As this is the structure, if you will, in the ionosphere, that's going to cause rapid changes in phase, and the receiver or the system doesn't necessarily care if what's causing the physics of the propagation changes. It only cares if it sees rapidly changing phase. So it is a problem. But it's even more of a problem when the amplitude is changing as well, because when you have very low amplitude, very low signal to noise, it's very difficult to even measure the phase. And so the combination of phase and amplitude is the most important thing. This gives you an example just to show you what signals we're talking about for GNSS. This happens to be a GPSL1 signal, and you can see how stable the signal is. Then the scintillation starts, so you get this turbulence, you get this small scale irregularities between the satellite and the ground receiver, and you start to see these rapid fluctuations. And again, the satellite is not changing position very fast, but the ionosphere is drifting at roughly 100 meters per second. And so this diffraction pattern is sweeping over my receiver, sweeping across the sky between the receiver and the transmitter. And you're seeing these changes, you see the signal goes up as well as down. And this is the S4 that we use to characterize that. That's just the normalized standard deviation of the signal. So that's the standard index we use. And this is the accompanying phase. And you can see the phase is affected, but actually not as rapidly as the amplitude is. And this is sigma phi. This is the phase, the standard deviation of the phase with no normalization. So these are two parameters that we typically use to characterize the S4 and the sigma phi. That's how we characterize the scintillation, at least simplistically. And these intensity fluctuations cause problems with signal to noise, which makes it hard for a system to operate. And the phase variations are difficult to track. The GNSS tracking loops are tracking phase. So if it's changing rapidly, that can be a challenge. So the two combined make it hard for positioning, navigation, and timing applications using GNSS. So one thing I want to stress before getting any further is there's two things that are required, right? We have to have the irregularities. We have to have these changes in over small scales, which we only get typically when there's an instability in the ionosphere. But additionally, we need electron density. If you don't have sufficient electron density, that electron density that term is directly in the index of refraction. And so if the electron density is too low, then the changes in the index of refraction will be too weak to really cause much scintillation effects on the signal. And I give you an example here. The blue curve is the S4 you get from the weak scatter approximation for a 10% perturbation, a 10% density fluctuation as a function of the background electron density. And you can see the S4 on the blue curve shoots right up. Okay, so at 250 megahertz. But by the time you get to a GNSS frequency, 1.6 gigahertz, you see it's not until the electron density gets above about 10 to the sixth
Mm.
per cc that the S4 starts to increase.
Mm.
Is there a question? Okay. Anyhow, so the point is, just as a rule of thumb, for GNSS, you need about 10 to the sixth electrons per cc in order to really have enough density to impact the index of refraction. And that tends to be at around 50 TEC units. You know, the profiles are not always the same, but that's you're looking in this 50 or more tech units to get substantial GPS scintillation. That's a rule of thumb. And what that says is it's something that's going to be more prevalent during solar maximum than during solar minimum. That's really the point. And this illustrates it. This is for about 10, 11 years here, just plotted the vertical TEC, the S4, which has been scaled by 100 here, and the F10.7. That's the solar flux. And what you see is the solar flux, well, we don't control that. The sun controls that. Those are the black dots, right? So that's what the sun is doing. But look at the vertical TEC measured. And this is, again, this is for a particular month in Brazil. The TEC follows that very closely. As the TEC, as the F10.7 goes up, the TEC goes up quite closely. The background density of the ionosphere tracks F10.7 or sunspot number, and we know that. But correspondingly, the S4, this is, I think, the 80th percentile S4, tracks the same way. So it's following the background density. So it's not just the irregularities, but it's the background density that really determines what the strength of scintillation will be. And there's some variation, but you can see it's a pretty closely coupled system. So that's the two things you need: sufficient background electron density and irregularities. It's important. And this is one step further. It says, by the way, if you look at the positioning errors, is the triangles are the altitude errors, the circles are the horizontal errors. The altitude errors tend to be worse, but they also track solar. They track the F10.7 as well. So, you know, when F10.7 gets above a certain value, the density is going up, and now the errors I see associated with scintillation are also increasing. So, in a way, the solar flux controls the impacts on GNSS. So definitely, it's very much a solar maximum type effect. And the recent solar max has been quite interesting. We've seen a lot of new things, and we probably have about a year left. Unfortunately, we're going to be going into a solar min period. Not right away, but you know, it's coming, and so that's the time to try to get receivers fielded so that you have them available for measurements as solar max approaches. There have been a lot of magnetic storms, and I know some of you live in low latitude regions. Even in lower latitudes, people have been able to see the aurora and so forth in the last year or 2 years. There have been a number of storms. Certainly, the aurora has been visible from Boston and Washington and places like that. And that tells you there's something happening in the space environment, right? That tells you that you have particles precipitating. There's a visual signature that you get when they impact the atmosphere and they cause the air glow. Scintillation doesn't give us anything like that, right? We don't know when it's raining. You don't see radio waves, right? This green shadow here, or these green emissions are photons, and radio waves are also photons. They're just at a wavelength that our eyes aren't sensitive to. So what would it look like? Usually we show scintillation. It's this one-dimensional thing. You know, it looks like this. And that does give you information about what scintillation is, power versus time. But if we have the ability to look across the spectrum, we see that scintillation does affect the signal strength and phase as a function of time, but it also is a function of frequency. And as a function of frequency, it's not following a simple 1 over f squared or some simple dependence. This is diffraction. And so These are four channels from a satellite, each 5 megahertz wide. This channel is showing very little effects, whereas adjacent channels are severely affected by fades. And here's a channel that's basically split in the middle. It's got a big null in the frequency. And so this is a measure of the frequency dependence that you can see. So it's complicated. And you look across this whole spectrum, there's a lot going on here. I'm going to show you a couple of movies. The green, by the way, where you see green, that's where the signal is above the mean signal level. So those are enhancements, right? We get constructive interference due to diffraction. And of course, the dips are the destructive interference regions. When you get into the red zone, you're down below 6 dB. Your signal has gone down at least 6 dB. And of course, the noise floor is the gray here. So anyway, the S4 measurement is not a very good indicator of how strong the scatter is in situations like this. We use other parameters, the decorrelation time. That's a measure of how fast the signal is fluctuating. And the decorrelation frequency, which is a measure of how decorrelated the signal is, how fast it's varying as a function of frequency. So just to show you a movie, what this is going to be, this is data that was collected in Guam, also a low latitude region, in last year, about a year ago, actually. And the bar here is going to show where the spectrum, where this radio wave spectrum is recorded in time. This is a whole night that I'm showing in these plots. And what you see is the S4 is pretty high, and then it stays relatively high and drops off later in the evening. Sorry. Back here. Way. Okay, now this is running. So I don't know how well this is going to project remotely across the but we're looking at this portion. You can actually see this is what the two-dimensional power plot looks like. And here are these other parameters, but this is what the spectrum actually looks like as a function of time. And again, I don't know how well, this is probably changing too fast to show very well, but these are rapid fluctuations. There's some frequency variation, and yeah, as we move forward, we're going to jump ahead in time. Okay, I must have stopped it. To a period later. This is the decorrelation time. These are fast variations. It's going to jump to a period later in the evening where the decorrelation time is quite long. In other words, we're getting very slow fading. This is all variations of scintillation. So you have this fast fading, things are changing with frequency, and in the same evening, you can get into an environment where things are changing more rapidly. I'm going to jump ahead. Okay, so now I've jumped to this portion, and now you can see how slow the fading is. Over 10 seconds, I get these fades. Now the signal's slowly building back up. And I'm going to get, a high period. And so different effects can occur from these different characteristics of scintillation. And the S4 in both cases is about the same, but it's a very different scattering environment. So for some systems, a very long, slow fade is more damaging than rapid fading. Now I've got this nice signal enhancement happening. It's very slow, but the signal is actually quite a bit higher than it would be in the absence of scintillation. And then it starts to fall off again. So it's kind of like this roller coaster just going up and down slowly, as opposed to the rapid variations. So these are very different scattering environments. There's a lot of dynamics in the scintillation, and the impacts on the system can be correspondingly different. Yeah, this is actually an interesting event. This is a where we had a storm, and there's actually a reversal in the field, so the things slow down, really slow down, and we see the same effects, the same scattering pattern, basically over the course of a minute, and that tells you how stable the ionosphere is. The reason scintillation is varying is only because it's drifting, typically so fast. But I'm going to step over this because this is more the same thing. This is, again, there's a reversal point. And I'll just show you this. This is the power pattern. These are the same irregularities. This is the same focus zone here as it is here. The signal actually reverses and drifts the other way here. This is due to the changes in the electric field caused by a storm. So the ionosphere is actually very stable at even these kilometer scale irregularities over the course of a couple of minutes. So the pattern is slowly changing if you want to think about what's happening in the ionosphere, but it's the drift that causes the dynamics of the signal when observed on the ground. I know some of you, most of you maybe, I hope I have seen this before. I'm going to play it again just because I think it's really important to show what does this signal do? What do these changes do? And this is a GPS receiver reporting its position over here on the right. Once a minute, the time steps, there's 60 data points. It's reporting once every second. You can see it moves a little bit, but it's pretty stable. On the left here, you can see the number of satellites that are scintillating as a function of time above a certain threshold. And when we get into the scintillation window, you can see what happens to the position. And the upper left is just telling us how many satellites the receiver was using to get that position information. So these are horizontal errors that you're seeing, variations within a minute of the positions reported by the receiver. And you can see this would be a huge problem if you're trying to land an aircraft or even drive a car in this environment using GPS guidance. These are 75 plus minus 75 meter error bars. So this is a stationary receiver. The positions it's reporting are jumping all over the place caused by the scintillation. And then as the night settles down, we get fewer and fewer satellites scintillating. The position error starts to calm down and the receiver behaves like it did before, showing pretty stable, slowly varying position errors, which is what we normally expect from a GNSS receiver. So this is happening frequently at low latitudes, and we'll move on. I just want to show that was from 2000. Here are GPS positioning errors from the past solar max, the most recent between 2013 and 2014. And this is showing the variation with the anomaly structure. Okay, this is just data from 3 GPS receivers plotted here, showing the TEC over a week. And there's no modeling or anything. This is just plotting the numbers. The position shift a little bit, and the plus and minus 20 degrees magnetic is shown by these dashed lines here. So the anomaly sits typically at about 15 degrees magnetic, so it's inside here. But this shows you, if you look over here, these are the magnetic latitudes of the sites and the errors they reported. This is all from South America, with the exception of Ascension, which is off the coast. And what you see is you get large errors. These are just normalized errors out to about 20 degrees. And so even stations that are outside of the anomaly, they're still looking at satellites that are pointing back through this high density region, right? Two things we need for scintillation. We need irregularities, but we also need sufficient density. And the anomaly really provides that density. Right at the magnetic equator, in fact, the GNSS errors tend to be rather low because this is post-sunset. This is local time here. Sunsets here, the density goes down near the magnetic equator. Away from the equator, you still have these very strong anomaly regions where the density is high. And so as you go to higher magnetic latitudes, you see that the errors really increase. Eventually, when you get to 23 degrees, now you're outside here. You've got a few satellites that are looking back through this region, but generally speaking, the errors are starting to decrease. But this just shows you how even within low latitudes, there's a lot of variation in the level of effects that you see on systems. And you have to understand what the physical system is that you're modeling in order to understand why. And this is just to share that these data, these errors were collected during this portion of the solar cycle, right? Compared to previous solar cycles, much weak. Remember that density goes up as solar flux goes up. And if we look at the current solar cycle, unfortunately, I didn't update this, should have. We see that the current solar cycle is a bit stronger, and we're seeing some pretty substantial effects on receivers. And this is a continuous process of monitoring because the signals are, the technology is changing, the receivers are changing. You've got more constellations available now. And so we have to be sort of continually monitoring what are the impacts, where are they most severe, and how can we help mitigate them. So this is just showing you the regions where the effects of scintillation occur, and there's effects at high latitudes on satellite communications and GPS. And I mentioned that this is mostly phase scintillation. It's dominated by fast phase variations. By far, the most important region in terms of the severity is the low latitude post-sunset equatorial bubbles, which you know about. And then at mid latitudes during storms, we've seen effects on a number of days. We have about 30 events so far in the current solar cycle going back to 2022, where we've seen significant scintillations at mid latitudes, often overlooked. But this region, these regions at low latitudes during the nighttime have such a routine occurrence that they're by far the most important in terms of potential effects on systems. This is a climatology of that taken from the DMSP satellite. And it just shows for a previous solar max, what the fluctuations or the percentage of perturbations looks like as a function of day of year and longitude. And you see this longitude, the solid lines here are telling us, based on a simple model, when we would expect the peaks to be, and they're largely correct. But interestingly enough, in the African sector, there is no real off season. There's activity throughout the year, and it doesn't really follow our simple model for why that should be the case. So there's much to be understood there. And similarly, if I take data from RockSat, which is another satellite, and again, this was measuring in space the fluctuations in the plasma density as a function of quarter of the year. This is March equinox, June, September, and December solstice. And you see that in South America region, during December solstice, that's where the global peak is. But the rest of the year, the peak is pretty much sitting over the African continent. And you can learn a lot from the space-based measurements, but you really need ground-based observations in order to get a good understanding of how this is behaving on a day-to-day basis. You don't get that kind of persistent monitoring from space. So statistically, space gives us a nice picture, but it doesn't tell us about the dynamics. And so Babatunde mentioned the SCINDA and SCINDA systems. We at one time had a number. We started in 2006. And the triangles here are GPS, where GPS data has been collected. The blue dots are GPS and UHF measurements, which are useful because the UHF sees a lot of activity even at solar minimum. And so we can use it to continue to monitor the atmosphere. But in any case, a lot of these receivers have not been functioning for quite a while. And this was very old technology now, the Novatel receivers, et cetera. So we need to update this. And I do think starting in this fall, that we will be able to start refreshing some of these systems, but probably not more than 1 or 2 per year. I think that's what we're going to be able to do internally at ISR. But we do have a plan to do that. So we're excited to try to get measurements reestablished and to particularly at locations, specific locations especially. But anyhow, that is part of our plan. All right, I mentioned space-based monitoring. Why is space-based monitoring important? Space-based monitoring is very important because A, it allows us to measure globally, right? Over the oceans where we never can have measurements typically, or we get very few measurements from an island here or there. And we do this through radio occultations. And radio occultations, I'm not sure what the future of radio occultation is, to be honest. If you asked me a couple of years ago, I would have guessed that in 10 years, we'll have thousands upon thousands of radio occultation measurements. I'm not sure that's going to be the case. So I'm reserving my enthusiasm a little bit, but we have developed some very powerful methods for using radio occultation to detect irregularities and locate those irregularities in space, which is a very challenging thing for the following reason. A radio occultation is basically, suppose you have a low Earth orbiting satellite, so it's flying at maybe 500, 700, 800 kilometers around the Earth. The ionosphere is this slab, if you will, located at about 300 kilometers. And the LEO is listening to a GPS satellite, which is thousands, 20,000 kilometers away at least. So that satellite is quite distant. As this satellite flies around the Earth, the signal it's receiving in time is occulting. That is, it's moving down in the atmosphere. It's cutting through the atmosphere, and eventually it'll fly over the shadow of the Earth, right? And that's when it's completely occulted. But until that time, it scans down through the atmosphere. And if there are bubbles or irregularities, that signal will be passing through those irregularities as the satellite moves along. The problem is this path is a few thousand kilometers because of this low elevation angle. It's a few thousand kilometers through the F region of the ionosphere. So the question is, well, where are the irregularities? I can measure scintillation on the satellite. That's easy. But where are the irregularities? Much more challenging. And these irregularity structures tend to be, 100-kilometer-ish scale sizes. So to locate those on a long ray path is a challenge. We develop techniques that use propagation theory. So using a phase screen propagation theory. We back propagate the wave. I'll talk momentarily a little bit more about that. But we're able to measure actually geolocate on these structures using the occultations. And this is actually a gold image, a UV image from a satellite that shows these dark shadow areas are nominally the regions where the bubbles, the low latitude structures, are occurring. That's the depletion in the background density that's associated with these structures that grow. You can't see the small scale irregularities. This is becoming impossible to use the mouse. But this shows you the regions where we have identified irregularities all from a satellite traveling down here and listening to a GPS signal way off the map here. So the satellite track is down here. The tangent point, that's the closest path to the Earth, is here. And we've identified the irregularities here, which correspond with these structures. And you can see how well the signal lies along this structure here. All of these are detections in the same structure, essentially. And we back here, the signal path was passing too high to detect the structures. But anyway, that's what we do. And there's a lot of these passes happening. I have references, won't go into the theory, but basically we're modeling the scattering and using phase screen theory. And the key thing is to take the measurement that you have and then propagate the wave backwards and look for the minimum in the scintillation. That minimum in the scintillation actually gives you an idea of where the phase screen is located. That's most likely the region where the irregularities are. This is detailing the theory a little bit more. I'm going to move through this. This is showing what you actually measure on the satellite. You get the phase and this SNR, and the phase is what we use to build the phase screen. This is what we start with as a phase screen and then back propagate the wave. And this is as a function of frequency back propagation of the wave. And there's the minimum amplitude fluctuations that you get. And we do it in frequency because the Fresnel frequency is a combination of the distance to the satellite, but also the magnetic field geometry. And so there's a couple of reasons why this is the most efficient way to do it. But essentially that tells us the distance from the satellite to those irregularities. And that is what we use to do the geolocation. And again, I'll show you another example here, bubbles that were identified. We've got statistics on this, looking at like 10,000 geolocations. This is the distribution of the errors using those images as a way to validate where the irregularities actually were. And so what you find is that 90% of those have less than 1 degree error. That's 100 kilometers. And 95%, so 2 sigma, fall within 2 degrees. So on these ray paths that are several thousand kilometers long, we're localizing the location of that turbulence to within a couple hundred kilometers with very high, good statistical accuracy. So that's been a powerful thing. And to show you what that looks like, this is just an example for a particular day in 2023. The terminator is the nighttime is where the bubbles are showing up, the structures, if you will. We're taking these geolocations and we're expanding them into structures. And there, as you can see, across Africa. So all of this can be correlated with ground-based data. And this was January, which is a time when there's usually lots and lots of activity over South America. You see we don't get any detections during the day, which is consistent. We're not seeing the irregularities. But this is all using Cosmic 2 radio occultations to generate these maps. And we do this in near real time now on a routine basis. Okay, sorry, I'm not going to have time to go into this, but the problem is you could identify where the irregularities are. You've got a horizontal geometry, but we want to translate that to an overhead geometry so that we can model what the user on the ground would see, essentially, or near the Earth's surface. And so that requires converting from a geometry like this, where I'm at a slant path through the F region, into an overhead geometry. Unfortunately, I don't have all the information I need to do that. It's under constraint. And so we do have another algorithm that we have to make some assumptions about the thickness of this region. This is Charlie Carano's work. It's very, he could give a seminar just on this topic easily. But basically, if you can assume the thickness of this, then you can make some other assumptions about the dependence of the irregularities on the background density, namely that the fraction or the percentage of delta n over n is constant through the layer, and then you can modulate with the background density. So by making a few assumptions, it's possible to do this conversion and calculate what the turbulence is for an overhead link based on your horizontal observation and translate it to a parameter that's useful to a user that predicts how much scintillation they would see from an overhead satellite, basically. So we go from horizontal to vertical, and there's still work going on this algorithm, but it's been applied to a bunch of a large number of occultations, and you can see if you that the error bar is something like 0.2 in S4 units. On raw measurements, mapping everything to the equator, that falls to about 0.1. So it's not as accurate as ground-based measurements when you do this. And again, we know that there's a number of assumptions that have gone into this calculation. But the point is, you can do it at a level that is still providing a meaningful measure of scintillation strength for a lot of systems, but does not negate the need for ground stations that anchor all these measurements, as many as we can get and are needed. So, and this is just showing you, here are a bunch of bubbles. We see lots of disturbances, but here are the ones that are strong enough based on the lambda disk. So if you were using a ground-based sensor, you wouldn't see these green. You might not see this, but you would see these red ones. So that's why you need lambda disk. You can't take every geolocation because the sensitivity of occultations because of those long slant paths is quite high. Okay, so I'm going to recommend that you at some point invite Charlie to give a seminar for more details on this. He's really done a great job. So I'm going to probably wrap up here, actually. I'm not really going to get into talking about the forecasting, it doesn't look like. So we still need to understand what the impacts are on GNSS. And as I say, that's an evolving situation because the technology is always changing and the new constellations make a difference. There's still plenty of room to think about mitigation algorithms. And one of the things I'm aware of, I know folks in Brazil are actually discarding the disturbed links. So when the S4 increases above a certain value, they're shutting off that link. They're not using it in the receiver. They've got a software receiver they're testing this with. And just throwing away the garbage link actually helps. So as long as you have enough links available, which you may not in all cases, that actually improves the performance they've found. Um, and there are more systems out there that can be affected. So, Starlink, for example, mostly uses higher frequencies, but we are aware of satellite communication systems and certainly non-space applications. And one of the things that really showed up during the storms that we had about a year ago today, the May storm, which was during a time when there's a lot of plowing and agricultural activity going on in the U.S. The GNSS they used GPS for guiding these tractors, and they were actually shut down for several hours, if not an entire day, which for large scale farming it was a big deal. It had substantial cost impacts. And then from the standard science perspective, we still don't really understand the longitudinal variability and the variability of variability. Why some places it's actually relatively predictable, in other places the day-to-day variability is extreme. As far as high latitudes, what instability processes? This is all work that's I won't say infancy, but it's much less mature than the work that's been done at low latitudes. And then again, during mid latitudes, at magnetics, during magnetic storms, what can we predict and forecasting? And forecasting is really the focus of our current phase of research. But I think I will leave it here based on the time. So thank you very much.
Wow. Thank you. Thank you. Thank you. Wow. That is a very high level presentation, Dr. Groves. That's really, really fantastic. Thank you for your time and I love the images. Like those are very, very nice images.
Yeah, I'm happy to make the slides available. I don't know if I can distribute those through you, Jonah, but if
Yes, I have just told them to put their emails in the chat box. So when you send it to me, I will distribute it to the group.
okay, all
And they
right,
also have
very
it
good.
recorded. If you don't grab all the presentation, um, I'm going to send the link to the YouTube database that we have, so you can listen.
Okay,
So it's really, really interesting presentation. So you can follow in a little bit slower steps.
yeah,
Yeah, but
yeah. Sorry, I
no,
apologize for
no,
that.
it's okay. That's really excellent presentation, and we want to thank you so very much for that. Is there any questions? Yes, Dr. Shigo.
Good morning. Morning, Keith. Morning, Jonah.
Yep.
Morning, and good day, everybody. Sorry, I'm not able to be on camera, but just a quick question, Keith. You had mentioned the growing use of occultation from space, right? But then you expressed reservation in terms
Yeah.
of its growth. And I just wanted to know why you think that it's probably not going to be as fruitful as maybe most of us would hope. I know there is always costs attached to some of these because most of the commercials going up there, they have the data, but obviously people have to buy the data to use it, and that may not be convenient for everybody. So I just wanted maybe you could further comment on that.
Sure, and it's exactly that issue. It seems like 5 years ago, Spire and Planet IQ and Geo Optics were launching satellites, preparing satellites, and of course we have Cosmic 2, which has provided that's over I don't know what the number, how many thousands of occultations they're up to, but it's only low latitudes. But the point is, the commercial market, I thought this was going to become a very ubiquitous technology. The main target there is terrestrial weather market, but Spire has pretty much stopped trying to support space science market with their existing products. They've I don't know if they've given up. I don't know exactly. But they've also, I know Planet IQ has just a couple, 3 satellites up or whatever, and it's not clear that the business model is there that's going to that's a big enough market that's going to support a number of players with a large number of satellites. And the guys that are flying are really focused on terrestrial weather products, which means that they're, again, with regard to Spire, I'm not seeing the quality of data that's needed to support the space weather products or they're not collecting the high rate data at the higher altitudes and stuff because there's apparently not enough financial incentive for them to do that. So it may not be right now it's just not quite as rosy. It appears to me based on the way the companies are reacting and the decisions they're making, as I would have guessed it was going to be a few years ago. So we'll see how it evolves. It may still prove to be a good commercial thing, but if not, I hope that governments decide to do it. That's all. I do hope occultations continue to increase and good quality data collected with them. But right now, I'm just not sure how the commercial market's going to go, and that's where most of the players are at the moment.
All right. Thank you very much.
Yeah. Thank you, Chigo.
Yeah. Any other questions? I like the scintillation weather kind of cloud, 3D cloud that you showed. And is that from one station?
Yeah, that's from a single station.
Oh, wow. You could do that for multiple stations as well. And can it be real time kind of?
Yeah, I mean, yes, you could do that in real time. It would be a little challenging to transfer the information that's required for those plots in real time because you need the full spectral measurement. And so instead of a single number, right, we record 50 hertz data or something on a single channel or a single frequency or maybe a few. But to get those full spectral plots, I think there's 4,096 channels essentially that we're monitoring simultaneously. So it's a lot of data to transfer if you have to do that in real time.
Yeah, and it's maybe computational expensive too. Anyway, yeah.
If you did it at the site and you just put out the video or something, then maybe that would be more reasonable. But right now, everything I showed, that was all post-processed.
Nice.